Anup sir. Hello. Anup sir. Hello.
Sir. Hello.
Anup sir.
Sir.
How many participants on YouTube?
YouTube, we have 10.
Okay. Shall we
We'll
start or we'll wait for?
Just a few minutes. We'll wait, sir.
Okay. Right. Anup is 1 minute wait చేయమంటున్నాను. We'll start actually, because there are around 50 participants in.
Sir, we'll start, sir.
Okay.
Sir.
Right. Singarvel sir, are you in the line?
Yes, sir.
Okay, we'll start, sir. Right. Good morning. Singarvel sir, audible now?
Audible, sir.
Right. Good morning. Warm welcome to all for 4th day of 1 week online FDP and optimization techniques for mechanical engineers, organized by Department of Mechanical Engineering, so Vigyan Institute of Technology and Science, so Deshmukhi, Hyderabad. So today we have 2 sessions. So morning session by Professor K. Venkatrao, Professor Vigyan University, Andhra Pradesh. So afternoon session at 1:30 by Dr. Kaushik Kumar, Bits Misra. And now let us go to the morning session. So I wholeheartedly welcome today's resource person, so Dr. K. Venkatrao, Professor Vigyan University, Andhra Pradesh. In spite of his busy schedule, sir accepted invitation as today's resource person. Thank you very much. I extend my hearty welcome to all participants for session 1 of 4th day's FDP. Now I request my colleague Dr. Singarvel to introduce today's resource person to all participants. So thank you once again to all, and now over to Dr. Singarvel.
Thank you, sir. Good morning to one and all. Myself, Dr. B. Singarvel, working as Associate Professor in Vigyan Institute of Technology and Science, Hyderabad. This 1 week FDP on optimization technique for mechanical engineers, day 4, forenoon session. Resource person, Dr. K. Venkatrao, sir. Once again, welcome, sir. Currently working as Professor in Mechanical Engineering, Vigyan Foundation for Science and Technology and Research, Vigyan University, deemed to be University, India. Sir has completed his bachelor degree from Bapatla Engineering College, Andhra Pradesh, the master degree from NIT, Tiruchirappalli, Tamil Nadu, and a PhD from JNTU, Kakinada. The sir have around 20 years teaching and research experience, and published 40 research publications. In that, out of 40, 19 SCI with highly impact factor journals, and the remaining are Scopus and other indexed journals, and also acting as reviewer more than 10 SCI journals. Under SAR guidance, 2 members completed his PhD and 5 members doing their research work. And also SAR received fund from DST with worth of 1.6 crore. And SAR delivered various lecture and invited talk across the India. Thank you, sir. We are one of resource person of this 1 week FDP on optimization techniques for mechanical engineers, which is organized by Vigyan Institute of Technology and Science. Please take over the session.
Sir, are you able to see this one? Hello?
No, sir. Slide, sir? Not it, sir.
Sir, you are muted, sir. Sir, please unmute.
Okay.
Okay, right.
Are you able to see this?
Wait a minute, sir.
Yes, sir. Yes, sir. Now it's okay.
Fine.
Maximize the screen, sir. Right, sir. Right, sir. Fine.
Can I start now?
Yes, sir. It's okay, sir. You can start, sir.
Okay. Good morning, all the participants. Before starting this session, I would like to say my thanks to HOD of Mechanical Engineering, Leela Prasad Garu, Dr. Chandrasekhar Garu, and special thanks to the Singerwell for his kind introduction of me to this presentation. One minute. Okay, are you able to see the screen completely, sir?
Yes, sir. Yes, sir. Yes, sir.
Okay, thank you very much. Today, my topic is power consumption optimization strategy in ball and milling of D2 steel via TLBO coupled with 3D FEM. But my topic, which was given on additive manufacturing, but many of the participants are not having the sufficient equipment to carry out their research work on additive manufacturing. I realized that most of you will do the research in the machining process, the equipment which is available to you. That's why I shifted to discuss these findings of ball and milling. However, there also I gave TLBO technique. Here also I used TLBO technique. Concept is same. There also I used the TLBO to optimize the power consumption. Here also I used the TLBO to minimize the power consumption. Based on the benefit of the participants, I selected this topic, that is power consumption optimization strategy in ball and milling of D2 stool using TLBO coupled with 3D FEM simulation, that is three-dimensional finite element modeling simulation. So before entering into the presentation, why this topic was selected, let us see now. So power consumption. So we know developing countries like India and Brazil, these kind of countries consuming the high amount of power in the production in the manufacturing sector. Since 2010, the consumption of power in this manufacturing sector.
Venkatrao, sir.
Yes.
Venkatrao, sir.
Yes,
Small
yes.
disturbance is coming, sir. I think it is fan sound. You can just verify.
Masai,
So small noise, sir.
fan apayamma. Now it is okay to you?
Now it's okay,
Sir,
sir.
is
Fine,
it okay
sir.
to you, sir?
It's okay, sir. Okay, sir. Okay. Thank you, sir. Thank you,
Let
sir.
me open it.
Right, sir. Please
Okay.
continue, sir.
Yeah. See, since 2010, the power consumption in manufacturing sector became, that is, consumption was increased 200%. So that is why it is required to minimize the power consumption in this manufacturing sector. So, and also if you not concentrate on reduction of the power consumption in the manufacturing sector, So it is hazardous to the environment also, because during the power consumption, so emissions like CO, CO2, NOx, these emissions are getting released and they are damaging the environment. So that's why, and with respect to cost also, and if you see in these power consumption in these developing countries, that share, that is in that economy of the country, share of the manufacturing in the economy of country near about 30%. So that's why it is very much required to optimize the power consumption in the manufacturing sector. It is one of the attempt is made using this TLVO technique in this one. And one more thing, why that D2 steel is selected as workpiece material. So D2 steel, it is high carbon steel which is used to make dies which are used in the forging, casting and other applications. So dies means all the dies are made up of with cavities. In that cavities, you have different types of complex cavities. So if you see the corners, there may not be having sharp corners. The corners may be curved corners. And complex shapes are also there. Miniatured products are miniatured products which are required to made with the dies. The cavity is complex. So far we have seen the plain end mill cutters. With this plain end mill cutter, if you see the bottom of the cutter, it is flat. So as it is flat, okay, it consumes less power consumption when compared with the ball and mill cutters. I will show the ball and mill cutters. After that, I will come again to the first slide. See this one. These are the ball and mill cutters at left side of the experimental design, where we have see bottom of the mill cutters are in the shape of curve. When compared with plain end mill cutters, where the bottom of the cutter is flat and the contact with the machine, that is workpiece for that mill cutters, is less when compared with ball and mill cutter. In this ball and mill cutter, you see the cutting zone, that is the teeth which are used for the cutting are in the shape of curve, are in the shape of round or curve. So when they are in the curved shape, there is a more contact between the workpiece and the tool. Whereas in the plain end mill cutters, if you see the contact area between the workpiece and tool is less when compared with this one. So that is why here it consumes considerable amount of power when compared with the plain end mill cutters. See, just before I told you, when you want to make complex shapes, complex cavities in the dies, we want to make complex shapes with curved shapes. With the plain end mill cutter, it is not possible to make the curved corners. But with the help of this end mill cutter, this kind of ball end mill cutters, it is possible to make curved cuts, that is cavities with curved corners, easily in that dies. That's why this one is selected in this presentation. Now, and next one is TLBO. It is one of the latest, that is teaching learning based optimization technique. One of the latest techniques used in the optimization. It is having some facilities. And this TLBO was developed by Ravipudu Venkatrao, R. Venkatrao. He is a professor in NIT Surat. He published more than 100 papers using this TLBO technique. What is the TLBO technique? Generally, this is teaching learning based optimization. This is more suitable for us to explain that one with the teaching concept. If we say, if you, okay, we are going to a class to handle one subject, okay, there are 60 members in that classroom. We conducted the mid one. After mid one, if you see the performance of the students, let us assume 20 students, that is 33% of students got less than 15 marks. And 20 students got marks from 15 to 20. Let us assume remaining 20 got marks more than 20 marks. So we classify the students based on their performance. Those who got more than 20, they are fast learners. Those who got between 20 to 15, medium learner, less than 15 marks. So they are treated as poor learners, slow learners. So we used to see this word slow learners, slow learners. So what we are doing in most of the engineering colleges, there is a counseling system, mentor system, and continuously we are monitoring the students. Those who have less than the marks, less than the 15 marks, we are concentrating on them. This teacher is a clever student, clever teacher. What he did, he identified the 20 fast learners and identified the 20 slow learners. Just he coupled them. So he paired them. So one bright student with one slow learner, he paired. Then automatically after 1 week or 10 days, if they have interaction between them, knowledge is transferred from the bright student to the slow students, for slow learner, and automatically in the second mid, third mid, in the end exam also, their performance will be increased. Similarly, overall class performance will be increased, and finally this teacher will be benefited with good performance in front of the management. You get the appreciation. Similarly, same concept was taken here. For suppose if you conduct 10 experiments based on the required outputs. So here let us assume the power consumption is our objective. If the experiments, for suppose out of 10, 5 experiments having low power consumption, 5 experiments are having high power consumption. By making the interaction between these two paired one like that, and poor experiments performance can also be improved. That is the concept of this one. So next one, we have used the 3-dimensional finite element modeling simulation. Why it was selected? So in this study, the optimization was validated with the 3D simulation. Okay, that is the overall concept of the work. Next agenda of this one is reduction of the power consumption. So various stages in the presentation, if you see, first one is selection of input parameters based on the literature. Input parameters were selected. Design of experiment, we have different design of experiments. Taguchi, RSM, where Benhan, CCD, central composite design, like that. We have different design of experiments. As per your requirement, you can select suitable design of experiment. Next one is optimization of process parameters to minimize the power consumption using the tlvo method. How it was selected, that one also we are going to see now. Next one is simulation using, we have many simulation softwares like ANSYS, DFORM, 2D, 3D, Advantage, like that we have. Finally, we are going to the conclusion. Now, if we see the ball and milling, just I shown you the shape of the ball and mill cutter. So, which is mainly used to meet demand in the production of micro piece based miniature parts like biomedical devices, automotive used in parts used in automotive industries, aerospace industry, and dies for forging and castings. Those things are made with the ball and mill cutter. So these ball and mill cutters are having additional advantage that just before I told you, complex shapes with good surface quality can be made. But there are some fundamental challenges with the ball and mill cutter with respect to the surface roughness, tool life, cutting forces, and overall efficiency that is included with the power consumption. So in high speed ball and mill cutting force is one of the important machining characteristics that has great influence on the other characteristics like tool vibration. Tool vibration results in tool failure and surface roughness also. And finally, cutting forces has major influence significance on the power consumption. So aim of this study, see this work already, the presentation which I am presenting here, it was already published in the measurement. which was published by me in a measurement journal in 2019. The power consumption. Next one. So what are the different optimization techniques used in manufacturing as well as the mechanical engineering? Taguchi method, response surface methodology, gray relation analysis, particle SAM optimization, genetic algorithm, simulated annealing, anti-colony algorithm. In addition to the 7, we commonly using other methods, that is graph theory and matrix approach, along with utility concept, and final one is the teaching learning based optimization technique. Now if we see the first one is the Taguchi method. So Taguchi method is a single response optimization technique. A simple example I will tell you. There is one turning process. In the turning process, we have 3 input parameters, say cutting speed, feed, and depth of cut. Cutting speed, feed, and depth of cut. The responses, that machining characteristics or output characteristics are, let us assume, surface roughness and cutting force. So we want to reduce the surface roughness as well as cutting force also. In the Taguchi method, you cannot optimize the process parameters combinedly for these two. That is called as multi-response optimize. It is not possible. So we can optimize the process parameters for the surface roughness, for the cutting force separately and individually. Separately, we can optimize the process parameters for the surface roughness, for the cutting force separately. For suppose, for less surface roughness, to get less surface roughness, if you optimize the process parameters, say you will get one set of process parameters. One set of process parameters we are getting. So these optimum parameters for the surface roughness are not optimum, may not be optimum for the cutting force, may not be optimum for the cutting force, where the cutting force may be increased. If you optimize the process parameters separately for the cutting force, at that particular optimum conditions, the surface roughness is not same. So to get the minimum surface roughness and minimum cutting force with a common optimum process parameters, it is not possible with the Taguchi method. That's why we should go for response surface methodology. It is a multi-response optimization technique, where in the multi-response optimization, for suppose let us assume there are same example, surface roughness and power consumption, surface roughness and power consumption, you want to minimize. For minimization of these two, you will get one common optimum process parameters. So here it is possible in response surface methodology, and in the gray relation analysis also. What the gray relation analysis it will do, that two output characteristics, the surface roughness and cutting force, are combined into one response. That will be integrating the two responses, not only 2, 3, 4 also. If there are responses, all the responses are combined into one response, and with respect to that one, it optimizes the process parameters. Similarly, in the response surface methodology, there may be more than 2 output characteristics. With respect to that one, the process parameters are optimized. But thing is that in that response surface methodology and gray relation analysis, in these two, what happening, that surface roughness and power consumption, cutting forces are given equal weightage, 0.5, 0.5. So where equal weightage was given. My intention is that I don't bother of the power consumption. So I have money. I need more quality of the product. More quality of the product I need. For more quality of product means the surface roughness should be less. So I want to give high priority to the surface roughness, say 0.7. Next priority 0.3. Priority I want to give to the cutting force. It is not possible there. It is not possible in the response surface methodology, gray relation analysis, genetic algorithm, particle sum optimization, ant colony, and simulated annealing. In these four methods, it is not possible to give weightage. So you have one method, utility concept. In the utility concept method, we can give the weightage manually, but scientifically we will not give. Okay, for suppose if you have two output characteristics, surface roughness and power consumption and cutting forces, we can give one value. So 0.6 for the surface roughness, 0.4 for the cutting force. But if there are more than 5, say let us assume 5 output characteristics, how to give the weightage to the 5 output characteristics? So scientifically, we have to simply randomly we cannot give. Scientifically, we have to estimate the weight to the individual output characteristics. So in all these methods, it is not possible. For that one, you have that is graph theory and matrix approach method is there. Using that method, we can estimate the weights to the output characteristics scientifically using preference graph. So that one also we have. Agarwal, he is a retired professor at IIT Delhi. After that, S. Manoj Seema, he is a professor at IIT Uttarakhand. They developed that graph theory and matrix approach to estimate the weights to the responses or output characteristics scientifically. I also followed them. I published 2 papers. One is in measurement, one paper in the that is measurement 3.37 impact factor, journal of alloys and compounds. There also I published 2 papers I already published. Not 2, 3, another one at CIRP, Journal of Manufacturing Science and Technology, using that GTMA along with utility concept. That finds that solution there. And one more difficulty with all these optimization techniques, say for suppose we have different output characteristics, say surface roughness, tool wear, cutting forces, power consumption, like that. My aim, I want to get surface roughness. It is constraint. The surface roughness should be less than 1 mm. And tool wear should be less than 0.3 mm. As for ISO standard, I am talking. So for one particular application, the surface roughness should be less than 1 mm. That tool wear should be less than 0.3 mm. These are my criteria. These things should not be crossed that values. With keeping these things as constraints, we want to reduce the power consumption and cutting forces. With respect to that one, the input parameters are to be optimized. No optimization techniques which are shown in this graph will satisfy these conditions. Taking some responses as criteria. Okay, response surface methodology, gray relation, Taguchi, these are well-known techniques for us. So in that one, what we are taking during the response surface methodology, all that is for suppose surface roughness, we are keeping minimum as target, minimization, tool wear minimization, cutting force minimization, power consumption minimization, material removed at maximization. So like that, we are giving the criteria to that one, but no specific value we are not giving to that one. So that particular thing. So in the response surface methodology, we have an option of that target values to the outputs also, but there is no guarantee that it will cross, it will satisfy that criteria, the target. It will get close to that one, not exact value will give. At least for suppose, if you want to get the surface roughness less than 1 mm in response surface methodology, if you give target as 1 mm, that output value after machining, after optimization or machining process, if you see, the roughness may exactly 1, it will not come, that is sure. The value may be less or more. If the value less than 1 mm, there is no problem, very good, fine. If the value got more than 1, or suppose 1 mm, if you got 1.25 mm, so it is not reaching the target value. So that is the difficulty in the response surface methodology. So that's why there are many complexities during the optimization process that we do not know. So all these complexities during the optimization or overcome in this teaching learning based optimization technique. So next let us see the modeling techniques. 1 second. Where we have different modeling techniques like Taguchi is one kind of modeling technique, RSM, regression analysis, FEM-based simulation. Next one is mathematical modeling, mechanistic models, and artificial neural networks. Except fourth one, FEM-based simulation, remaining 6 are data-based modeling techniques. Data-based modeling techniques. And if you see the sixth one, mechanistic models, they are semi-analytical mathematical modeling techniques. Sixth one also we can skip from that one. 1, 2, 3, 5, 7 are completely data-based modeling techniques. What is the modeling technique? What the modeling techniques will do here? They develop relation between inputs and outputs. Say outputs are surface roughness and tool wear and cutting forces. So inputs, if we say cutting speed, feed, depth of cut, tool nose radius and tool rake angle. Let us assume 5 inputs and 4 outputs. So here these modeling techniques develops a relation between inputs and outputs separately. That is some equation it gives in terms of input. See, for suppose if you see the surface roughness, where you will get one equation in terms of the inputs. So in terms of input cutting, that is, for suppose if you see the RA is equal to C0 plus C1 into cutting speed plus C2 into feed plus cutting C2 is constant into depth of cut plus C another that is C4 coefficient constant into that input value. Like that you will get the equation. So these equations are generated, developed using the experimental data which was collected conducting the experiments. So we have some set of inputs as per design of experiment. We conduct the experiments. During the experimentation, the surface roughness, the tool wear, cutting forces, metal removal rate, other responses we are collecting. So we are taking this one in the form of table, inputs and corresponding outputs, and we put this one, if it is Minitab, if you put that one in the Minitab, the Taguchi method, RSM, they develop the relation between the inputs and outputs. Similarly, mathematical modeling, we can develop regression analysis, mechanistic models, and even this artificial neural network, which is part of machine learning technique, there also it develops the relationship between inputs and outputs using the experimental data. That's why all these things are called as data-driven modeling techniques. Now, fourth one, if you see, that is finite element modeling based simulation, where it is not like that. It is physics-based modeling technique. What is the physics-based simulation? If you see in that all the software simple, most of you are aware of the ANSYS. In addition to that one, in the machining process, in addition to the ANSYS, we have the abacus, and we have deform 2D, 3D, and advantage softwares like that. We have different types of softwares where we have in the softwares you have to select the what is the input material, what is the tool material. That is workpiece material and tool material we have to select, and in that softwares you have the material library. From that one you have to select the mechanical and physical properties to the workpiece and tool, meshing and remeshing, number of elements, size of the elements, like boundary conditions, inputs, all the things you have to define there. After that one, if you run that simulation, you will predict all the outputs like cutting forces, thermal distribution, stress distribution, formation of chip, all these things, even the spring metal, that is elastic recovery, all those things we can estimate or predict using the finite element modeling technique. So like that, see, if you see all the database except FEM, remaining all things, they take very less time. In minutes we can do it. Once if you put the data in that software like Minitab or EasyNN plus MATLAB, if you put the data and set the inputs and outputs, if you run, within 5 minutes you can print. But FEM, it is not like that. This is physics based. It runs the program inside using the physics equations, and it estimates the outputs. That's why it is taking time. Sometimes it will take days also. But they have some advantages, disadvantages. If you want to focus the mathematical modeling, what you will do? It is very fine like that. You will tell it takes less time. It predicts accurately when compared with that one, like that you will project. In your research, if you want to project the FEM-based simulation, you will raise this one. It is so good in that way. It gives accurately. Like that, you are elevating the FEM-based simulation. So they have some limitations and advantages. So based on our requirement, we elevate the advantage. That is depends on our application. Okay. Fine. These are the modeling techniques. So from the optimization, as for our requirement, we selected tlvo, that I will explain. Next one, for simulation, we selected the FEM-based simulation. In this one, we have taken EasyNN plus, that is advantage software for the machining simulation software we selected, which is easy. That's why I selected these things. Now you see this one is teaching learning based optimization. This is in some application, okay, that these tlvo methods are able to handle complexities in the optimization. So this one, this slide I already explained. So how the tlvo works. First, knowledge is transferred from teachers to student, that is called as teacher phase. After that, knowledge is transferred from good students to poor student, that is called as learner phase or student phase. Like that optimization takes place. Now this is finite element analysis, already told. In this work we used the third wave advantage software to predict the machining characteristics. Now this is the flow chart of this total presentation, design of experiments and experimentation. That one also in the next slides we will tell. What are the response characteristics, that is output characteristics we acquired. So that is first one, Fx, Fy, Ra, and vibration of amplitude of cutter vibration are measured. PC is cutting force is estimated using the cutting forces. Next one is tlvo, initial population is defined. After that we have teacher and learner phase. Next one is combined population. From where we are selecting the best one. And finally we have the simulation. Using that simulation, that output characteristics are estimated and validated the optimization. Umasai? Umasai? Panic. Say, in this power consumption, in this graph, I am presenting the estimation of power consumption. You may get one doubt that we can directly measure the power consumption during the experimentation. Very good, fine. With wattmeter, we can estimate the power consumption directly. But here is problem is that in the CNC machine, there are many subsystems. So not only machining process. See, generally during the machining process, cutting forces will be developed. For that one, some power is consumed. Not only that one, if you see to move the table in X and Y direction, it additionally, that is not related to the machining. So it consumes some power. Okay, you can include that power because while machining we are moving the table. That's why we can include the power consumption for the table movement in the cutting process. No problem. But if you see the coolants, to supply the coolant, we need some power consumption is required. To change the tools, we need some power consumption. To operate the control, some power consumption is some system is required that consumes the power. Other than the machining, there are other subsystems like coolant supply, control systems, tool change. All these things will also consume the power. These three power consumed in these three areas also included in the power consumption if you measure directly. So I don't want to include that elements. That is why I estimated the power consumption using the cutting forces. See here, during the machining process, cutting forces in X and Y direction are measured using a force dynamometer. Everybody knows the dynamometer, which is able to measure the cutting forces during the machining process in the X direction, Y direction, and Z direction. Okay, at this present war, is corner and effect of the force in Z direction is negligible. Why the cutting force in the Z direction is negligible? Let us see now. The tool, this is one kind of end milling process. When the tool is moved, see this, once again I am saying this is end. This work is performed when it is moved from one end to other end. There is no force in the Z direction. Very negligible amount of force you will see in Z direction. That's why that is neglected. That is why your force is neglected in the Z direction. So here we measure the cutting forces in X and Y direction using the dynamometer Fx, Fy, and see this one. Anywhere if you see the power is estimated as product of cutting force and the velocity. See this one. Here the tool, this is the circle is nothing but cutter. This is end mill cutter. Rotate here, it is rotating in clockwise direction. Not only rotating, and the rotating cutter is moving in X direction with velocity of Vf. Vf is the feed velocity. In addition to that one, you have the velocity of cutter. The cutter is rotating. For that one, we know how to estimate the cutting speed of that one in terms of meters per minute. Pi dn by 60, where d is the diameter of that one. Diameter of the cutter. N is the RPM of the cutter. Using that one, we can estimate the VC. As this cutter is rotating, we cannot define the direction of the cutting speed. See this one here, you have the tangential to this one. So that's why the VC, that is cutting speed of this cutter, is resolved into X and Y direction, VCX and VCY. So now if you resolve this one in X direction, total velocity you will get to VF and VCX. In Y direction only you have VCY. So how you get the VCX, VCY? If you know theta, then you can find out VC sin theta is the velocity element in X direction. VC cos theta is the velocity dimension in Y direction. See this one. The average thickness of the chip was obtained at 45 degrees of cutter rotation. Then the power, you will get the average thickness at the 45 degrees of cutter rotation. That's why power consumption was estimated at 45 degrees of cutter rotation. Now you come here, you say here it is 0 of cutter rotation. This one is the 90 degrees of cutter rotation. At 0 of cutter rotation, the chip thickness is 0. At this 90 degrees, the chip thickness is maximum. At 45 degrees, the chip thickness is uniform. That is, you can take the average value of the chip thickness at theta is equal to 45 degrees. That's why we have taken theta as 45 degrees. If you take the theta is equal to 45 degrees, all the things we know. Fx is measured with the dynamometer, VC is estimated using the diameter of cutter and RPM, and VF is also, this is input value, that is uncut chip thickness, that is feed for tooth. Also we know all the things are known, then easily you can estimate the power consumption. Now we see in this experimentation how we measure the forces and amplitude of cutter vibration. See this one is experimental setup. So this is Chandra Plus production vertical machining center. In front of this one laser Doppler vibrometer is placed. This is non-contact sensor which is used to measure. This is used to measure amplitude of cutter vibration. Generally, in most of the places, we have facility of accelerometer. The accelerometer is used to measure the amplitude and frequency of cutter vibration. Not only amplitude in terms of the vibration is measured in terms of amplitude, acceleration, and root mean square of vibration velocity. In different ways, we can measure the vibration of workpiece using the accelerometer. Similarly, in the laser Doppler vibrometer also, we can measure the vibration in terms of displacement, velocity, acceleration, and the root mean square of vibration velocity. In different forms, we can measure even in the LDV. Now, specialty of LDV, let us see. Okay, so during the machining process, we can measure only the vibration of workpiece because it is stationary. It is not rotating. In this milling machine, the workpiece is fixed on the table. That's why it will not rotate. It is same. It may move in the X or Y direction only. So, for suppose if I want to measure, okay, and one more thing, if we want to measure the vibration during the machining process using the accelerometer, for suppose length of the workpiece, let us assume 100 centimeters, 100 centimeters, not mm. So 1 meter length we have. Okay, we one end, the machine place the accelerometer at this end or that end. At any end, there is a distance of the accelerometer to the machining center is 500 mm. So actual vibration cannot be measured with the accelerometer. Whereas if you see, and one more thing is that to measure the vibration exactly at the machining area, we can measure the vibration of tool because at the machining area, the tool is removing the material. If the tool is rotating, on rotating tool, the contact sensor, that is accelerometer, cannot be placed. It is not possible to place that one. That's why with the LDV, where it produces a laser beam, which is non-contact sensor, the laser beam is focused on the rotating body. From that one, it measures through that laser beam, it measures the amplitude of tool vibration during the machining process. It's the LDV, it seems to be very simple. Cost of that one is around 18.5 lakhs, which was purchased under PST project, imported from the German. So where you have the dynamometer, using the dynamometer, forces are measured in X and Y direction. See this one. Next, let us see the experimental procedure followed in that process. See, experiments are conducted using the mill cutter, which is with the 2-fluted carbide ball and mill cutter. Each experiment started with the new mill cutter. Say the LDV, which is Polytech 100V type laser Doppler vibrometer, which is used to measure amplitude of tool vibration during the machining process. Next one is the Kester 9257B type dynamometer used to measure the cutting forces during the machining process. After machining, the workpiece, the tool and the workpiece were removed. Then the surface roughness on the machine surface is measured, was measured using the Mitutoyo 178923E as a 210 type profilometer. So after that one, all these things, that is the experimental results which are collected and estimated are placed in the table. FX, FY, are measured using the dynamometer. Vibration amplitude is measured with the help of with the help of the laser Doppler hygrometer. RA is roughness is measured with the Taylor profilometer, where we shown that one. And PC is the power consumption is estimated using the equation 1. See this one using this equation 1 at 45 degrees of cutter rotation, where you have the average thickness of this chip. That's why where we estimated the power consumption, that values were taken here. Now we are going to the optimization process. So this one is the measurement of the vibration. See, the first one is the time domain. Next one is bottom one is the frequency domain. In the time domain, this is acousto-optic emission signals, which are directly measured with the LDV. From that figure, you cannot measure, you cannot see anything. So what is the value of amplitude at what frequency? We have more amplitude that cannot be seen directly from the time domain. So that is what we did. That is AOE signal, that is acousto-optic emission signals, which are processed using a fast Fourier transformer. That fast Fourier transformer process that time domain signals and converted into frequency domain, where we can directly read that one. See this one. This is the red line in the bottom figure. The red line which indicates the maximum value of amplitude, that is 60 mm. See this one where this is 59.80. See this 59.80, I didn't put as by seeing this figure. At the right side of this figure, that was cut in this figure. At the right side of the figure, it gives the value also. What is the maximum value of displacement and at what frequency? See at x coordinate, see this one around see 750 hertz of frequency. You have the maximum amplitude. That values will be displayed. You don't bother of that one. So that values are taken in this one. So this is about the measurement of vibration during the machining process. Now, so we have the power consumption, RA value, Y value. See this one. Now we go to this one. Fx, Fy are included in the PC. Fx, Fy are included in the PC, estimation of PC. RA measured, vibration also measured. So finally we have the three output characteristics. Now our aim, we want to minimize the power consumption. Not only minimizing the power consumption. So the vibration should not be more. The vibration should not be more than 16 UM as per ISO standard. As per ISO 10816, amplitude of cutter vibration should not cross 16 UM. And as per ISO 1302 for that particular application, the surface roughness should not cross the 2 micrometers. These constraints, see this one, constraints. Y and RA. Y is nothing but amplitude of cutter vibration, RA surface roughness. A should not be less than that particular values as per ISO standards. So how these equations we got? How these equations were obtained? So this table, see this one, this table 3, this data simply you place in the Minitab 17, 16, 18, 19, whatever the version. You put this table there, you select the inputs and outputs. If you generate, you will get these equations in terms of the inputs. For the PC, RA, Y, we got the mathematical equations in terms of VC is cutting speed, feed, depth of cut, like that we have. And finally, we put the constraints, Y, RA as constraints. See this one, during the optimization, the cutting speed should not cross 15. That is, should be within that limits, 15 and 30. It should not be less than 15, should not be more than 30. Similarly, feed also should not be less than 100 UM per tooth and should not be more 300 UM per tooth. Depth of cut also should not be less than 15 UM and should not be more than 200 UM. These are the constraints. What are these parameter bounds? If you see, when we are interacting, when you allow interaction between the students, see this one, knowledge is transferred from one student to another student. general condition is that intelligent student, the fast learner, is 24 hours of time, he cannot concentrate to him. He will set some time. So for this particular student to whom I am the mentor, I have to minimum 2 hours or minimum 1 hour. I have to give coaching to him, and it should not cross 3 hours. So I can spend time between 1 to 3 hours to him. So the mentor, that fast learner, cannot spend more than 3 hours, and at the same time he will look after that the coaching should not be less than 1 hour. Like that, the parameters bounds were set. So here in this experiment, this is machining experiment based on the previous literature, especially not only based on the previous works, based on the capacity of machine. Capacity of machine, these parameters are bound. Sometimes the machine may capable of running the machine more than 5,000 RPM also. But if you not only even 50,000 RPM also we can run the tool. So if you run the tool more than that one, power consumption will be more, some other complications are there. That's why we optimize. Within these two limits only, that parameters are bound. So these are the conditions, initial conditions for the optimization. I think all you understand this one. PC, that is equation, that is mathematical relations, that is linear equations. So you can get out that, sir, you have taken only linear equations. Why can't you go for quadratic and other things also there? No problem, you can go for that one also. Quadratic equations can also be taken. So luckily, when I got these linear equations, the R square value is around more than 95%. That's why I have taken these linear equations. There is no problem. If the R square value is less than 80 or 70, no, we cannot use these linear equations. Based on the R square value, whether we have to take linear, quadratic and other type of equation to be selected. Okay, everything is fine. All the things we set here. Now we go for the optimize. This is the initial phase. All of you. See, I am saying the participants that the TLBO technique is a very, very important technique. With this, you can produce very good papers with high impact journals. Myself, with this TLBO technique, I produced 4 papers in SCI journals. Among my 20 SCI journals, 4 are TLBO method. So the first paper which I shown, that is the TLBO technique published in the measurement whose impact factor is 3.36. So with high impact factor journals, you can produce with this teaching learning based optimization technique. Once again, I am explaining. So from here, at least you listen very carefully. It is very advantage to you, those who are doing research in the, especially manufacturing or in other techniques also. Even some of our colleagues, they used this TLBO technique in that is heat treatment. That is heat transfer in thermal field also. They used it at IITs. And they got good papers and they submitted their decent got degrees also. Okay, now this is the starting step of the TLBO method. See this one, all the inputs VC, F, D. These are the inputs. RA, PC, RA, Y are the outputs. So here 1 to 15, these are the experiments. We are assuming that all the experiments are students. All the experiments are assumed to be students. These responses, power consumption, RA, Y, are assumed to be subjects. What is the target of the student? He wants to reduce the power consumption, RA and Y, by different students, 15 students. Criteria, This is for the constraint for RA. 1 minute. Okay. ZRA is constraint for surface roughness. ZY is constraint for Y. Z dash is the overall constraint. You need not to confuse. Constraints for RA and Y and capital. So why these constraints, how these constraints have been obtained here? If you see, here we have the constraints. Y should be less than 60. RA should be less than 2 newton. What I did here, you see, ZRA is equal to Y minus 60. ZRA is equal to RA minus 2 newton. How we did, you see in this one, see this one, ZRA is equal to RA minus 2. So 2.2 minus 2. See this one. So here we have the RA constraint is 2, less than 2. So that is why this RA 2.02 minus 2, now you got 0.02. Similarly, 2.97 minus 2, you got 0.97. In this way, we are estimating. Now, if you come to the experiment 7, 1.17 minus 2, where you will get minus 0.83. Here, minus 0.83 will come. Negative values are taken as 0. So here also minus 0.05, that we have taken as 0. Now if you come here, minus 0.3 taken 0. So here if you see minus 0.57, it is taken 0. Here also negative value minus 0.07. That's why all the negative values are taken as 0. Positive values are kept as it is. Similarly, here also ZY, see 59.80 minus 60. See this one, constant is 60. So negative value will come, that's why we have taken as 0. Similarly, 68.32 minus 60. So you got 8.32. Negative values are taken as 0. Positive values are put as it is in that column. Next one, overall constraint. See, among all these constraints of RA, maximum value is 1.93. Keep in mind, 1.93 is the maximum value in ZRA, and similarly 15.41 is the maximum value among all the ZY values. With this one, how we are estimating the overall constraint? See this one, Z dash is equal to ZRA by ZRA maximum plus ZY by ZY maximum. So ZY maximum is 15.41, that from this table. ZY maximum, ZRA maximum is 1.93, that is from this table we taken. Now see this one, ZRA by ZRA maximum, ZY by ZY maximum. Here now 0.02 by, see this one, 0.02 by 1.93 plus 0 by 15.41, you will get this value. Similarly, for the next row also, 0.97 by 1.93, 8.32 by 15.41, between them we have the plus. So 0.97 by 1.93 plus 8.32 by 15.41, you will get value of 1.0425. Similarly, overall constraint we have taken here. So what we meant this one, 0 values indicates that there the surface roughness is less than 2, and Y value is also less than 60. That 0, Z dash 0 indicates that completely the constraints were satisfied where the roughness is less than 2 newton and vibration is less than 16 newton. The constraints were satisfied. So that's why they were given first rank, 111. So based on the quantity of that one, so remaining ranks are also assigned 2, 4, 2, 3, 4, 5, 6, 7, like that we give. This is the initial phase in the teacher phase. I think all of you understand. Same thing will continue in the next steps also. 1 or 2 things we will add. Very simple. If you listen, it is very simple. If you feel difficult, we cannot understand. Very simple. Simple arithmetics only I am telling here. In the total TLVO simple arithmetics. That is subtraction, division, addition. That's all. Not more than that one. No complex equation, no complex analysis. Only thing is that you have to listen here. Sorry. Now in the table 4 itself, at the starting average value of VC, FD, that values are estimated. Average VC is 23.55, average F is 15, 150, average value of D is 75. Mean values were taken. I told you that the interaction depends on the time. The time should not be 1 hour, should not be more than 3 hours. So those are the parameter bounds. So now if the fast learner gives coaching to him at 1 hour, so what is the performance of the slow learner? If he concentrates 3 hours on the slow learner, how his performance will be increased? That is what we are seeing. That is interaction time we are changing here. How the interaction time changes? That one method he introduced here, that is, see this one, we have to identify, we have to calculate the difference underscore mean for the cutting speed, feed and depth of cut. For the 3 inputs, that is for the 3 inputs, you have to estimate the difference underscore mean. So here formula is there, you don't bother of that one, all the formulas available. R into X minus X bar. What is the R? R is the random number. You can select any value between 0 to 1. So in this study, we selected random numbers 0.89 for the cutting speed, 0.75 for the feed, 0.41 for the depth of cut. Like that, these random numbers were selected for the 3 inputs. So R is random numbers. X is, we know, that is input value. X bar, already I told you that mean value. How to estimate difference underscore mean? With example, I will explain. See this one, difference underscore for the mean, difference underscore mean for the cutting speed, 0.89 already we selected here, and you can take any value. In reverse order also, you can take 0.41 also, it doesn't matter. Whatever the value you wish, that value you take. So here I have taken 0.89 into, see this one, X minus X bar. So now you go to the previous X, this one is 18.84 minus X4, 23.55. That thing only I put here. 18.84 minus 23.55. Nothing I put. As for data available in the data, same thing I put here. Similarly for the next one, 0.75 is the random number, and X minus X bar. Now you see, what is the X here for the feed? 100 minus 150. See this one, 100 minus 150. Similarly, for this one also 100 minus 75. That is what I put here. 100 minus 75. Random numbers already we explained. So if you estimate that one, you will get difference underscore mean for the cutting speed, feed, depth of cut. See this one, minus values we got. Minus 4.19 for the speed, minus 37.5 for feed, 10.25 for the depth of cut. Now what we have to do? So new process parameters we have to identify. That is new time, how much interaction time, that is to be estimated here. Simple, these different underscore mean values are added to the inputs in the table 4. See this one? See this one, 18.84 plus minus 4.19, you will get 14.65. Where you got this 18.84? See this one, 18.84. Here we have 2, this one, difference underscore mean. Similarly for the hundreds also, difference underscore mean values were added. So if you add this one for the VC, that is cutting speed, you have 14.65. New feed, you got 62. new depth of cut, you have the 110.25. So intavariki bagana. So far it is good. A small thing I will tell. So cutting speed is 14.65. Now you come here, parameter bound. So cutting speed we got 14.65, but here parameter bound we have 15. That is why you have to take 15 only. See this one, 15 we have taken here, new in the table 5, 15 we put. Now for the feed, if we see 100 plus minus 37.5, you will get 62. It is less than the parameter bound, less than the parameter bound. That is why we have to take 100 here. That we have taken 100 here. Now if you see here D1, so if we add the difference underscore mean to the 100, so we get 110.25. If you see here, that is within the range. That is why it is not required to change. Say the values which were taken. So these two values are not same. 15 and 100 are not same. Actual values are 14 and 62.5. As they crossed the minimum limits, as per our requirement, minimum values we should not take. We should take the minimum values, not less than that one. That's why we have taken 15 and 100. That's why we put A at bottom. You see the values have crossed the limit, hence the bound values were taken. Similarly, these difference underscore mean values are added to the all the experiments, and we get the new process parameters in the table 5. You see for the experiments 2 to 15, all are new process parameters. If they cross the limits, we put A. That indicates that they crossed the limit. So this here we have the new input parameters. For the new input parameters, you have to identify the power consumption and surface roughness, Y values using the equation 2, 3, 4. I think all of you understand. So new process parameters we got here, and using that new process parameters, they substituted in this equation 2, 3, 4, and we get the power consumption, surface roughness, and the amplitude of cutter vibration. That is why where you got the new inputs and the corresponding outputs also. ZRA, ZY, Z dash, we know already, we explained. So RA minus 2, Y minus 60, negative values are taken as 0, positive value taken as T's. And this value Z dash, that is overall constraint, is also estimated based on the value of Z dash. Ranks were given. So total up to 7, where we have in the next step simple table 4 and 5 are combined. This is called as combined population. Next only one step I will tell, it will close. So next one, that is table 4. Before new inputs and after new inputs, these two tables have been combined here. So from this table, the experiments which are having first rank, all those things are identified and kept in that table 7. So this, see this one, total 15 experiments were taken. So as it is starting, we have the 15 experiments. That's why we have taken 15 experiments. In that, among 15 experiments, 13 are first rank. That constraints were satisfied. That power consumption, that is not power consumption. RA is satisfied, less than 1. Y is less than 60 in the 13 experiments. In the 14 and 15, okay, one Y is satisfied, RA is not at satisfied, okay, no problem. So for further also, you can doubt that, sir, however, the constraints were satisfied in the 13 experiments, why can't take that 13 experiments as best? But our target is not to meet the constraints. Our target is to minimize the power consumption. So when you minimizing the power consumption, the two constraints are to be satisfied. That is the criteria. So though we got that satisfying the criteria, we cannot go for conclusion. So with that first ranked experiments, which experiment is having less power consumption, that we want to identify. For that one, we are going for the interaction. That is, I told you, pairing the students. Similarly, interaction is carried out. So that interaction can be performed between any two experiments. So here, randomly we can go for interaction. So here, experiment 15 we can take experiment 1 that can be interacted with the remaining 14. Where interaction between 1, 2, 1, 3, 1, 4, 1, 5 up to 115, like that also. So here we follow the interaction like this: 1, 2, 15, 2, 14, 3, 13, 4, 12, 5, 11, 6, 10, 7, 9, 8, 1, 9, 2, 10, 3, 11, 4, 12, 5, 13, 6, 14, 7, 16, 8. One order I followed. For you, it is not required. You can follow any type of interaction. You can take 15 that will be interacted to all the things. So no particular rule for this one. Whatever you wish, as per your wish, you can follow the interaction. How we go for interaction, let us see. This one also very simple. This equation is available. You need not to develop. See this one. Let us see the interaction between 1 and 15. So new VC is equal, cutting speed is equal to VC1, and the value of cutting speed in the first experiment, into A1. A1 is again random number. You can take any value. So between 0 to 1, no need to follow this one. Whatever you want, 0 to 1 you take. And the next one is VC1 minus VC15, because where we carried out the interaction between 1 and 15, that is why VC1 plus A1 into VC1 minus VC15. Similarly, feed also F1 plus AT into F1 minus F15, D1 plus A2 into D1 minus D15, where the A1, A2 values are random numbers, and VC1 from the table, see this one, 28.27 minus 19.37. That is what is put here. But next one is 100 is that is F1 plus random number 0.7 into 100 minus 112.5. That value similarly for D also. If these values are within that parameter bound, that value will be taken. If they crossed minimum side or maximum side, that bound values were taken and placed in the table 8. See this one. So for 1 to 15, you have the see this one, new inputs. For the new inputs, corresponding PCRA Y values are identified using the equation 2, 3, 4. So in that one, the new input parameters are substituted, and you will get the substitution. Means you need not to take the calculator and do all the calculations. We have Excel sheets. You develop the Excel sheets. In that Excel sheets, once if you develop the formula, if you click and column wise, you will get the values. No problem of that one. See this one. So similarly, ZRA, ZY, Z dash, same, and 0 values are given, 1 rank 1, and accordingly ranks are given. Again, table 7 before interaction. This is table 7, and after interaction you have the table 8. These two are combined. That's all. So table 1, that is before interaction, after interaction, the two tables are combined. You got 13. In the 13 experiments, you selected that 25 experiments. So 25 experiments are having rank 1. In that one, 25 experiments are having first rank. That's why 21 experiments were taken from the 30 experiments. From that 21 experiments, see this one, 25 experiments. 25 experiments. 20, see 1 minute. You got up to 28, sorry. You have 28 experiments. Total, not 21, 29 is also there. You can see here. Among 30, right. See, first rank, we want to select the first rank. We have number of first rank experiments. Among these first rank experiments, see, the first rank experiments, literally they satisfied the two criteria. Surface roughness is less than 2 nm vibration is less than 16 mm. Among all these things, which is having less power consumption, that will be selected. So finally, we got from that one 29 among the 29 experiments. See this one, 3 experiments are having less power consumption. See this one, experiment 5, 24 and 9. So why I directly came here, between these two you have CCS technique, that is central crowding, central crowding distance sorting technique. CCS, central crowding distance sorting technique. Now you come here, how to estimate the crowding distance, CD for PC, CD for RA, CD for Y. So first all the PC values, see this one, all the, 1 minute, 1, 2, 3, 4, 5, 6. See this one. So in this one, 21 experiments got 1 rank 1. From 30, you have 21 experiments. See this one that you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21 experiments having rank 1. See first, these experiments are arranged as for PC, arranged in ascending order. All these things are arranged in the ascending order. So highest values are given infinity value. So it is cut here. See this one, now you can see. For the power consumption, experiment serial number 11, 16 having least values. Experiment 1 is having highest value. So least values and highest values are given infinity. Similarly, for the RA also, all the RA values are arranged in ascending order, give least value and highest value. Y also arrange in ascending order, assign the least value with infinity, assign the highest value with infinity as the crowding distance. How to estimate the crowding distance for the remaining things? You see here you have the formula. You don't confuse. I will explain in detail. Estimation of the crowding distance. You have to estimate the maximum value, minimum value of PC. 58 is minimum value. 126 is the maximum value. See, to estimate the crowding distance for the experiment for serial number 23, see this one, for this one, 67 minus 58. See, I want to estimate the crowding distance for 63. For this one, previous slide, if you say, okay, PC 9 minus PC 26 by PC maximum minus PC minimum. See, now is in the next slide. See this one. For this one, PC 9 minus PC 26 and before and after values. Before and after values. See this one. PC 9 minus PC 26. See this one. PC 9 is the before, that is more than 63, and the next less than 63 is 58. So that's why 67 minus 58 divided by 126 minus 58. See this one, PC maximum minus PC minimum. So like that we estimated crowding distance for all the experiments, for all the serial numbers, and finally overall crowding distance estimated. This one is overall crowding distance added here. So overall crowding distance here, based on the central crowding distance sorting technique, we estimated, we found 3 best solutions. 3 candidate solution, means best solutions we got. So that is at PC values these things, RA values condition satisfied, less than 2 nm, Y values also less than 60 nm, and like that we have these three are estimated as the optimum working condition. The TLBO suggested 3 optimum working conditions. Now we have to validate this one. So in this process, just 5 minutes I will close it. I don't take much time here. Say here we used simple I am going third wave advanced software we have taken. So in that one we have in other softwares like ANSYS and other things we have to design the you have to design the workpiece and tool. That design means specifications, workpiece meet, all those things are to be defined. It is not like the ready-made tools are there. Simply you have to give the values. What is the diameter of that one? What is the length of shaft? What is the radius of ball, and what is the helix angle, rake angle? That simply if you type, that will take and give the ready-made tool, and if you carry out the machining process, and finally we can predict the cutting force in X, Y. I don't take much time here, and as the time crossed already, I think 12:30 crossed, right? Okay, amplitude of cutter vibration is also measured, that is predicted using the software, and all, and experimental also at this working condition. These 15, 24, 9 are the optimum working conditions. At these optimum working conditions, experiments are also conducted. Now here if we say that RA values, Y values are less than 2 and 16 nm respectively. Power is also consumed. In all the cases, maximum you got experimentally you got 69 value, 69 for the 27 experiment, remain are 67 and 65. If you want, you can take 3 as optimum. So especially if you want to concentrate on the power consumption as minimum, experiment 9, so that is cutting speed of 15, feed of 112.5 and 80.25 as depth of cut. You can take them as optimum, and however the criteria are also satisfied. So these are the conclusions already concluded. Thank you. Any doubt you can please ask me.
Singer well.
Thank you, sir. Thank you for your step-by-step explanation procedure. Here we are having few questions, sir. One is how to fix random number in TLBO method.
It is up to you, whatever the value you take. 0 to 1, any value you can take. That name itself saying random number.
Sir, in milling process, up milling and down milling, there is any cutting force value differences?
That already we have in the actually we are looking for the up milling is giving metal removal rate. If metal removal rate is more, there you have the definitely cutting forces are more there. Where you have the high metal removal rate, definitely there you have the high cutting forces also. Obviously power consumption.
And which modeling technique gave good result in research?
That is up to you. Whichever you want to establish, highlight that one, you are saying this is best. So generally, actually, if you see, one thing I will tell you, if you want to publish a paper in Journal of Intelligent Manufacturing, there is that is Springer. It is acceptance rate is around 9%. 9% is acceptance rate. Springer paper, that is Journal of Intelligent Manufacturing journal, where it considers the papers which are written using the machine learning, like artificial neural network. Definitely what the author will do, he will establish the ANN, because he wants to highlight the ANN to publish his paper in that one. And if you want to publish a paper in the International Journal of Simulation and Theory, that one also SCI journal, where what you will do, you will highlight the this FEM simulation. So anyway, FEM simulation is best one as per my point of view. The people, as per the journal which you want to publish, which he likes, that we will highlight in our research work. As per my point of view, FEM is best because this is physics based simulation. If you see the ANN, mathematical modeling, other techniques, they are data-based modeling techniques. The data-based means the experiments which you physically conducted using the data, modeling we did. If you not performed well the experimentation, definitely that is wrong. Whereas FEM, it is not like that. You are selecting the workpiece material from the software itself. So you cannot hide or you cannot manipulate anything in that one. Only thing is that in FEM, it takes much time. That's all. So as per my point of view, FEM is best one.
Sir, one more question. Do the optimization technique give empirical formulas to use different optimal parameters arrived for particular process?
We are using that one. That's why we are developing the empirical equations. మనం డెవలప్ చేస్తుంది వాటి కోసం వీఆర్ డెవలపింగ్ దెమ్ టు యూజ్ టు ప్రిడిక్ట్ ది వాల్యూస్ టు ది ఇన్పుట్స్ వేర్ వీ డిడెంట్ కండక్ట్ ది ఎక్స్పెరిమెంట్స్ ఫర్ దట్ పర్పస్ ఓన్లీ వీఆర్ డెవలపింగ్ దెమ్ అంతేగాని ఫర్దర్ వీ డోంట్ హ్యావ్ ఎనీ యూజ్ విత్ దట్ ఎంపెరికల్ రిలేషన్స్ సే ఫస్ట్ ఆఫ్ ఆల్ యూ కెనాట్ కండక్ట్ ది hundreds of experiments. You simply ask for design of experiments. What is the concept of design of experiments? You want to conduct less number of experiments instead of conducting large number. For suppose if you one particular set of, for suppose if you take the 3 inputs, input 1 cutting speed is 3 levels, input to feed is 3 levels, depth of cut is 3 levels. So if you see the full factorial design, you will get the 27 experiments. But as for design of experiment, it suggests only 9 experiments. So if you want to know the values for the remaining 18 experiments, what you will do? You will take that equations. In that equation, you substitute these inputs and you are getting the outputs. That's all. For that only we are using the empirical equations. Right?
Thank you, sir. Thank you, sir. Then I will hand over to Dr. Devaprasad, sir.
Good afternoon, sir. It was
Good
nice.
afternoon, sir.
It was a nice
good
session. Thank you
sir.
for thank you for your complete detailed explanation.
Thank you, sir.
And since we have another session at 1:30, which is scheduled,
Yeah. That's why I closed.
so we have to allow participants to take their lunch.
Yes.
With due respect from our Vignan Institute of Technology and Science and Department of Mechanical Engineering, all the staff here, we thank you, sir, wholeheartedly, and also
Thank you,
from
sir.
our participant side.
Thank you.
With this, with this small vote of thanks, I will request all the participants to join us by 1:30. Thank you, sir.
Thank you.
Thank you.
Yeah, we'll close here and we'll join at 1:30. Thank you.
Right.